Welcome back to this General Chemistry 1 lecture. Today we're going to be carrying on with trying to determine the sort of compositions of atoms and elements and molecules and compounds and so on and so forth. So we're going to be building on the sort of materials that we saw on Tuesday, such things as like we discussed what an atom was, how in terms of chemistry, we're most interested in the three particles, which are neutrons, protons, and electrons. Neutrons are neutrally charged and are generally given about 1 atomic mass unit. Then the other two particles, they are oppositely charged. One is proton and one is an electron. The proton is positively charged and the electron is negatively charged. If you have trouble remembering which one's which, just try to remember that protons begin with P and positive also begins with P. The electrons tend to have very, very small masses, and the protons have a mass of around about 1. So usually whenever we are talking about a particular element or an atom of a particular element, in order to determine its mass, we usually only consider the protons and the neutrons, because the electrons have a negligible impact on the mass. On top of that, the protons and neutrons are located within the nucleus. The number of protons in the nucleus is given a special number called the atomic number. That atomic number is sort of the identity of the element. If that atomic number changes, i.e. the number of protons change, then we have a different element. We don't have the same element anymore. So for example, hydrogen doesn't have any neutrons in its basic form. Carbon has 6, boron has 5, aluminum has 13, and so on. Those elements are defined by their proton number. So they could have different numbers of electrons and different numbers of neutrons, but so long as their atomic number, i.e. the number of protons, remains the same, they are going to be the same element. Now, if the number of neutrons does change, we have a special name for that, and it's called an isotope. So for example, hydrogen has 3 isotopes. It has protium, which is the most common form, which we usually use the letter H for. Then there's deuterium, where we have 1 neutron and 1 proton. So it has a mass of 2, but still only has a mass or an atomic number of 1. And then we have tritium, which has an atomic mass of 3, but an atomic number of only 1. So the key defining feature of those isotopes is that they only have 1 proton, and so therefore they're all hydrogen based. Then if we have different numbers of electrons, we have what are called ions. If we have excess electrons, we have a negatively charged ion, which will be an anion. And if we have a deficiency of electrons, then we will have a positively charged ion, which is called a cation. So there's a few different special names there. Don't worry if they're not totally familiar to you yet. They will become much more familiar as you go through General Chemistry 1 and General Chemistry 2. What else? We also covered molecules and compounds and ionic compounds as well. So molecules were things like H2O, water, which was made up of 2 hydrogens and 1 oxygen. Then for ionic compounds, we could have sodium chloride, which is our common table salt. So it is made up of sodium, the sodium ion, which is positively charged, and the chloride anion, which is negatively charged. And so that brings us on to how we name those things. Like, for example, a positively charged sodium atom is a cation, which is called the sodium ion. Whereas, for example, the chlorine atom, if it were to become an anion, that is to be negatively charged, then it would be called the chloride anion. So usually with regards to naming conventions, we take the root of the word for the anions and add ide, so chloride, oxide, fluoride, and so on. Whereas for the positively charged ions, we usually don't do that. So like sodium ion, calcium ion, and so on. That's kind of like a brief sort of 3 or 4 minute summary of what we did last time. So today we're going to start with section 2.6, and we're going to be talking about the concept of the mole and molar mass and their application. On top of that, we're going to be looking at the use of the molar mass of an element and Avogadro's number in calculations. Then we're going to try and use that to calculate the molar mass of a compound from its formula and a table of atomic weights. And then we'll calculate the amount, i.e. the number of moles of a compound represented by a given mass, and vice versa, using Avogadro's number to calculate the number of atoms or ions in a compound. So we probably won't get section 2.6 finished today. It's a big section. There's a lot to it. So let's discuss it and try to make sure that it's totally clear. So a mole is a unit of counting things. So it is the counting unit for atoms, molecules, and ions. So you can have a mole of atoms, you can have a mole of molecules, and you can have a mole of ions. A mole has a specific number. It is 6.02 times 10 to the 23 of those things, like atoms, molecules, or ions. This number has a special name as well. It's called Avogadro's constant. You may have come across that word before. If you haven't, you've got a new word. So this is a very specific number. It's usually given in like on your periodic table, there'll be like an Avogadro's constant given to you. But I mean, it's 6.02 times 10 to the 23, at the very least 6 times 10 to the 23. So the mole is the unit that we can use to count these things, these atoms, these ions, these molecules. It's a very, very big number. So we use it to count really small things, atoms, molecules, and so on. Avogadro's number is what it's called. So Avogadro's number, it's a really big number. It's like this much, which is a lot. So this is why we use scientific notation, because if you'd write out all of those zeros every time, it would take a long time. So it's the equivalent of the chemist's dozen. So for example, socks. We have a pair of socks, doesn't matter if they're size 5, size 6, size 7, size 8, they're still usually sold as a pair, which is 2. Eggs, we usually get in a dozen, which is 12. Pencils, you might get in a gross of 144. Paper in a ream of 500. And beer in a case of 24. And then atoms or molecules, you get a mole, which is 6.02 times 10 to the 23. So this is a common measurement unit, as is the case for these other items. So Avogadro's number, it was named after Amedeo Avogadro, who came up with it, who discovered this concept and applied it to different systems. He was around quite some time ago. He determined that the number was this number, and we'll find out in a minute just exactly why that number is the number that it is. And so there is Avogadro's number of particles in a mole of any substance. So this is important. So if you have a mole of carbon, you have a mole of hydrogen, you have a mole of silicon, you have a mole of magnesium, you will have the same number of particles. They may weigh differently, they may have different masses, however, they will be the same number of particles. So counting the mole. Chemistry is a quantitative science. We need a counting unit, the mole. So we need to keep track of all of our masses, all of our times, all of our temperatures, in order to be able to reproduce the results that we have. Without that, we're not going to be able to get the same outcome the next time. So the mole is, 1 mole is the amount of substance that contains as many particles, atoms, or molecules as there are in 12 grams of carbon-12. So this is where Mr. Avogadro, or Amedeo Avogadro, got his value of 6.02 times 10 to the 23. It is the number of particles there that are in 12 grams of carbon-12. So for example, here we have lead pellets. So this is 518 grams of lead, which is about 2.50 moles. This shows you how we can use the unit. So for example, this many grams can be expressed as this many moles. 2.5 moles, 3 moles, 4 moles, we can have many different numbers of moles. Just depends on how much mass of a substance we have. Here, for example, are 1 mole amounts of different things. So sulfur has a relative atomic mass of about 32, and so 1 mole of sulfur is 32.066 grams. Magnesium then has the mass of 1 mole of magnesium is about 24.305. And for tin, it's 118.71. And for silicon, it's 28.086 grams. And then copper up here. These are all, these numbers you might notice are all the relative atomic masses of that element. And this is important because that is what a mole is. So carbon 12, 12 grams of carbon 12 is 1 mole of carbon. Sulfur 32, 32 grams of sulfur 32 is going to be 1 mole, and so on. And the same sort of concept will apply to molecules and compounds and ionic compounds that we see later. So molecular mass versus molar mass. So molecular mass of 1 molecule in atomic mass units, and molar mass is the mass of 1 mole in grams. So for example, if we have water, which is H2O, here it has a molecular mass. So the molecular mass is equal to 2 times 1, the mass of the hydrogen, plus 1 times 16, which is about the molecular mass of the oxygen. And so that will be equal to 18. Okay. And so that is the, why not? So that is the molecular mass of water. However, the molar mass is going to be the mass of 1 mole in grams. So that is based on this value here. So the molar mass of water is going to be 18 grams. That means that for every 18 grams of water, we have 1 mole of water. So that's 6.02 times 10 to the 23 molecules of water. So this cup contains a huge number of, let's say this is about 200 milliliters, maybe. So 200 milliliters say that that is 200 grams. 200 grams divided by 18. Anyone got a calculator? It should be around about 10, 11 maybe. Am I right? About 11? Anyone? 200 divided by 18. 11.11. All right. Very good. Thank you. Okay. So it's 11.11. So that would be, so my coffee mug filled with water contains about 11 moles of water. So it's 11 times 6.02 times 10 to the 23 molecules of water, which is a ridiculous number of things. Molar masses then, so note that the mass of water is included in the molar mass of a compound for these ones. So for example, here, this is copper dihydrate, so it includes the water in the mole. So it's like copper chloride plus, so it's like, in order to get the molar mass here, it's copper plus 2 chlorides plus 2 water molecules. And that's how you get this. Aspirin here doesn't include any water. So you can see here at 180.2 grams is 1 mole. Here 170.5 grams is 1 mole of copper 2 chloride dihydrate. Here we have iron oxide, which has this formula. And so this is its mass of 1 mole. And then water, for example, which is something we just talked about a moment ago, it is H2O and it has about 18.02 grams per mole. And so there's about 18 milliliters here. So that's about 18 grams of water. That is 1 mole of water. So the mass of a mole is going to be the same as the molecular mass, or so the molecular mass in grams per mole. So like this one. The molecular mass here in atomic mass units directly converts into the molar mass, but this time in grams. So 1 mole is equal to the formula weight in grams. Right? That's what I just said. Of atoms, molecules, or ions. So atoms like sulfur, molecules like water, ions like sodium ion or chloride. So we can convert between these pretty easily. We can convert moles to mass and mass to moles. So if we have the number of moles already, we can multiply that by the grams in 1 mole. So that's like, for example, say it's water. Say we have 1 mole of water, and then we put, it's 18 grams per mole, so 18 up here. So 18 times 1 is going to be 18 grams. It's the same calculation as we did earlier. Here, if we want to convert mass to moles, we have to go in the other way. So say we have 18 grams of water again, and we multiply that by 1 mole over 18 grams, which is the molar mass of water, and we would get 1 mole. And down here, you can see the example as well. So if we have 16.5 grams of carbon, how many moles is that? It is 1.37 moles of carbon. So make sure you check your significant figures always. So for example, these are, this 1 and this 12.01 are what are known as perfect numbers. So they don't affect the significant numbers or the significant figures in your answer. And so only this number, which would be given to you or measured experimentally, is useful in the calculation of significant figures. So note that 4 significant figures are used in the molar mass, but there are 3 in the sample mass. So you use the lowest number of significant figures, which is 3. So that's 1.37 moles of carbon. So here's another example. So how many magnesium atoms are there in 150 grams of magnesium? Use the molar mass of magnesium from the periodic table and Avogadro's number. So 150.0 grams of magnesium is what we're told. The molar mass of magnesium is 24.305. You can get that from the periodic table, which you will always have access to, at least in my quizzes and tests. So here's 150.0 times 1 over 24.305 times Avogadro's number, which is 6.022 times 10 to the 23 magnesium atoms in 1 mole of magnesium. And so when we multiply all of this out, so we cancel the grams per milligram with grams per magnesium, grams of magnesium, moles of magnesium, and that leaves us with these numbers being multiplied together, magnesium atoms. And so the answer will be 3.717 times 10 to the 24 magnesium atoms. So I'd encourage you to try and do this with like another element and see if you can do it. Make sure that it's all kind of familiar in your mind, and that it's very easy whenever I go through this and talk about it. It's all very obvious, but later on when you're looking at it, it might not be as obvious. So it's a good idea to review it straight after the lecture is done, if you can, and just do a different example. Do it with carbon, do it with chlorine or whatever. Yes, there's a comment or question. Somebody's asking me if we're allowed to ask for a copy of the PowerPoint. I'm not sure. I need to ask for this. Is not that this is, as you can see here, the copyright of the publisher. So it says it may not be scanned, copied, or duplicated, or posted to a publicly accessible website in whole or in part. Well, Canvas isn't really publicly accessible. I'll ask the publisher. Maybe.
Sir, I have a question.
Yes.
So for the number of sig figs, do we follow it based on the number of sig figs given in the question? So the sig figs of the question, it's 4. So the answer also has to be 4 sig figs.
Right. Yeah. So in this case, we use we have 4 significant figures because we have 4 here in the question. Like the numbers here are not going to affect the numbers of significant figures. So yeah, use the ones in the question. The question is your guide usually.
Okay, thank you.
So for example, here it's 3 significant figures because it's 3 in the question. Okay, good question, Kyle. Thank you. So how many grams of chromium are there in 25.1 grams of chromium-3 acetate? So chromium-3 acetate has this formula here. Chromium-3 means that it's how many, what's the charge on chromium here? Anyone remember from the last lecture? You might be able to remember. Is it positive? Is it negative? Is it chromium-3? What's the charge on chromium-3? All right, someone give me an answer. +3, very good. It is indeed +3. That's what the 3 is about. So this 3 in Roman numerals indicates the charge on the chromium, which is +3. Very good. All right. So chromium acetate has this formula. So if we add together the mass, atomic mass of chromium and carbons and hydrogens and oxygens, make sure we account for the fact that there are 3 acetates here, we would get a number which is 229.13 grams per mole. This is important because in order to determine the number of grams of chromium, we're going to have to determine how many moles of chromium acetate we have. So the first thing that we need to do is determine how many moles of chromium acetate we have. And so this is what this equation here is. So this is 25.1 grams of chromium acetate. That's from the question, times the how many moles of it is. So 1 mole in this many grams. So this is what we calculated earlier. So 229.13. So we would get a value of about, let's say, somewhere in the region of 0.08 moles. And then from that, actually, I can just calculate it now. Let's see. Okay, so that's going to be, so for this part, we have an answer of about 0.1095. That's terrible, but 0.1 or 0.1095. Okay. Then, so that's the number of moles of chromium acetate we have. But now we need to find out what percentage of this chromium acetate is actually chromium. And so from that, what we're going to do is chromium has an atomic mass of 52. So this part here is going to become 52 over the 229.13. Okay, and so that is going to be something like 52 divided by 229.13. So the 52 you get from the periodic table, and the 229.13 you get from this calculation here. And so that is gives us an answer. So this then is, make it over here, be easier. It's going to be 0.2269. Okay. So this is going to be this number, which is the number of moles of chromium, times this number, which is the fraction of chromium acetate, which is chromium, times the mass of chromium, which is here, which will give us the total amount of chromium in our sample. So this is the fraction of chromium acetate that is chromium. This is the number of moles of chromium acetate, and this is the mass of chromium. So if we multiply this number, and this number together, we will get 5.70 grams of chromium to 3 significant figures. The 3 significant figures, remember, come from our question. We'll have other examples like this, but if anything's not super clear right now, just let me know. So here are a bunch of practice questions. I encourage all of you after the lecture, and once you see the posted lecture, to try these. Based on what we've talked about, these are all achievable answers. So you've got the question, you've got the answer. If you struggle to get the answer, just maybe try it again. And if you still can't get it, then let me know. Send me a photo of your working or whatever, and we'll see if we can figure out what the issue might be. Okay, so leucine is an amino acid. It's essential it's an essential daily dietary requirement for adults. It has this formula here, and 2.2 grams is necessary per day. So asked what is the relative molecular mass of leucine. So in order to get that, we would add we have 6 carbons, 13 hydrogens, 2 oxygens, and 1 nitrogen. So that's 6 times 12 is going to be the carbon contribution. So 6 times 12 plus 13 times 1 for for the hydrogens, plus 16 times 2 for the oxygens, plus 14 times 1 for the nitrogens. And so that will give us a value of 131, if I'm not mistaken. And then we're asked how many moles of leucine are required daily. So here we would have here we would have 2.2 times 1 over 131. So that's 131 is from here, which would be equal to 2.2 divided by 131 is going to be 0.01, but 2.2. So it's going to be 7. How many molecules of leucine are required? So it's going to be 0.017 times Avogadro's number. So 0.017 times 6.02 times 10 to the 23, which is equal to, this is really hard to write on this, is equal to what? 7 times 6.02 times 10 to the 23. It's going to be 1.02 times 10 to the 22. Okay, so then how many nitrogen atoms are present? So who wants to give me an answer? How many nitrogen atoms are present? If this is the number of molecules of leucine, how many nitrogen atoms are going to be present? So if we have 1.02 times 10 to the 22, sorry for my terrible writing, but how many nitrogen atoms are present? How many nitrogen atoms are in one molecule of leucine? Let's start with how many, like just that answer first. How many nitrogen atoms are here in this molecule? I'm going to ask somebody very soon if no one wants to give me the answer. How many nitrogen atoms are in that molecule of leucine? There's a guess, like you can tell me 10. It's fine. Just somebody give me some sort of an answer, please. All right, perfect. Yes, only one is present. Very good. Okay, So if I have one atom of nitrogen in every molecule of leucine, and I have this many molecules of leucine, how many nitrogen atoms do I have? Do I have the same number or do I have a different number? Yay, very good. We got the same number. Excellent. All right, nice work. Okay, we got there in the end. Good job. All right, give yourselves a pat on the back. So yes, we have the same, it's not a trick question, we have the same number of nitrogen atoms. So there is one nitrogen atom here. So we haven't totally talked about stoichiometry, but maybe some of you might have noticed that like these little numbers indicate how many of that particular atom there are in the molecule. If that was not really known to you, that's okay. Like we still haven't really covered that. But I was hoping that maybe some of you already knew that, which some of you did, which is great. And so we have this many molecules of leucine. And if there's one nitrogen atom in this many molecules, or then we have the same number of atoms of nitrogen. So for example, if it's the number of oxygen atoms, it would be this number times 2 because we have 2 oxygen atoms. For hydrogen, it would be this number times 13. And for carbon, it would be this number times 6. Carbon atoms, I've just told you. It is, in fact, this number times 6. Yeah. Okay. So which of the following elements has the largest molar mass? I've given you the relative atomic mass. So which one of these elements has the largest molar mass? Potassium K, neon Ne, arsenic As, iron Fe, silicon Si. Answers in the chat box, or you can even say it out loud, that's fine. Which one of these has the largest molar mass? If I have 1 mole of any one of these, which one weighs the most? Which one has the most mass? Yes, very good. I got an answer. The answer is, a few of you have written into me. This is the answer, arsenic. So AS, so very good. Yep, excellent. Potassium has a mass of 39 grams per mole, neon 20 grams per mole, arsenic 75 grams per mole, iron 56 grams per mole, and silicon 28 grams per mole. So the largest number here is arsenic. So arsenic is the one with the largest mass. Very good. So what is the approximate molar mass of iron oxide, iron 2 oxide, the 2 here, so it's 2 plus oxide. This is its formula. So which one of these is the approximate molar mass of FeO? Is it 56? Is it 72? Is it 896? These are the relative atomic masses of iron and oxygen. Yes, very good. Okay, a few of you have messaged me. Excellent. So yeah, so the answer here is 72. So we have iron, we have oxygen, so we have 1 of each. So 56 plus 16 is 72. 72 is the answer. Very good. So the molar mass of CH4 methane is 16 grams per mole. So that comes from the carbon, which is 12, and the hydrogen, which is 1, but there are 4 of them. So 4 times 1 is 4, plus 12 is 16. Okay, that's a good question. I'll discuss that. So yes. Okay. So the way that we calculate this previous one is in order to get the molar mass or the approximate molar mass, we have added together, okay, we have iron oxide. There are no subscripts here, so we know we have one of each. So one oxygen, one iron. So then we have 56 and 16. So for every one oxygen, every mole of for every 1 mole of oxygen, we have 16 grams of oxygen. And for every 1 mole of iron, we have 56 grams of iron. So if we add these together, we will get a value of 72 grams. And that is the same as 1 mole of iron oxide. So that's how we get the 72. It's usually just adding it together. So how many atoms are there? In this case, there's one of each, so add them together. And then, well, actually they're ions, but anyway, add them together, we get the molar mass of that compound. So the same here for carbon is 12 for methane, and hydrogen is 1, but there are 4 of them. So we multiply that by 4, and so we get a value of 12 plus 4 is equal to 16, which happens to be this one. So the molar mass of methane is 16 grams per mole. Remember, the mass one is the bigger number, the one at the top of the symbol in the periodic table. So which represents the greatest number of molecules in methane? Is it going to be 35 grams? Is it going to be 1.8 moles? Or is it going to be 12 grams? So your strategy here is to find out how many moles there are. You don't actually need to calculate the number of molecules. You just need to figure out which one of these represents the largest number of moles. So this one, you already know the number of moles, but how many moles are here and how many moles are in 12 grams? And then that will tell you the answer. So remember to convert mass to moles, you multiply by 1 over the molar mass, which is 16. So it would be 35 times 1 over 16. It would be 12 times 1 over 16. And that will give you the number of moles of this one and this one. And then we will be able to compare the number of moles, and whichever one is the larger will give the greatest number of molecules. Okay, so which one will give me the greatest number of molecules? 35 grams, 1.8 moles, or 12 grams? Okay, I've got one answer. I've got a lot of answers. Excellent. Okay, yes, 35 grams, because 35 is 35 times 1 over 16 times 1 over 16 is going to be equal to like 2.2 something, I think. I don't have a calculator right now. So that's going to be 2.2 moles. That's larger than 1.8. 12 grams is less than 16 grams. So we're going to have less than, so 12 times 1 over 16 is going to be equal to 0.75, which is the smallest. So this one is going to be the largest. Now, why did I say you don't actually need to calculate the number of molecules? Well, it's because in order to go from moles to molecules, you multiply by Avogadro's number. So whichever number you start off with, it's going to be giving you the largest number of molecules. So 2.2 times 6.02 is about 13 or 14. 1.8 times 6.02 is what, about 11, 10 or 11. 12 times 0.75 times 6 is about 4.5. So times 10 to the 23, of course. But hopefully you get the idea that like the part of this question is asking the greatest number of molecules, but really it's just asking you which one is the greatest number of moles. Yes. So if you got 35, that's great. If not, hopefully you see it now. If you don't, let me know. Okay. All right, so we're on to section 2.7 then. Express the composition of a compound in terms of percent composition. Determine the empirical and molecular formula of a compound using percent composition or other experimental data. So we're going to now use some of those skills that we've just learned to try and determine the empirical and molecular formula of a compound using percent composition or other experimental data. So percent composition is analysis used to characterize unknown compounds. So this is where our mass spectroscopy that we briefly talked about last time is useful. So the use of that is to determine the composition of unknown compounds. Percent composition data can be used to calculate an empirical formula. So percent composition is really it's a ratio of, it's just from mass, really. It uses atoms and elements, so maybe it seems totally different and unfamiliar, but really it's based on what should hopefully be familiar mathematics. So this calculation is not unique to chemistry. Calculate the mass percent or weight percent of each element in a compound. So the strategy here is to use this equation, which is just a fraction over or times 100. So here we have the formula weight of the compound. So this, say for example, we have water. So we're going to look at H2O. Okay. H2O that we've talked about a lot. So it's got what, 2 hydrogens. So I'm calculating right now the formula weight or the molecular weight. Formula weight just covers more classes of species. Times 1 times 16. This is the oxygen. And so that's going to be equal to 2 times 1 is 2 plus 1 times 16 is 16. So that's going to be equal to 18. So our formula weight of water is going to be 18 grams per mole. Okay. Or sorry. No, it's not. It's going to be 18 U. Okay. All right. So then say we want to find out the percent hydrogen in water. We would then want to find the atoms of an element, number of atoms of an element. So that would be equal to 2, because there are 2 hydrogens in water, times the atomic weight of hydrogen, which is 1, over the formula weight, which we calculated as 18 here. So that's going to be 18 times 100%. Who can give me the answer, because I don't have a calculator? Use your phones, your devices, your computer even. All right, 11.11. Seems like 11.11 is coming up a lot today. Thank you very much for the answer. 11.11%. That came up earlier. Okay, excellent. So this kind of calculation, as hopefully you've seen, is not unique to chemistry. It's really just a percent composition. So it could be like, for example, say you had a business and you wanted to calculate the percentage of your total profits that came from selling, say you're a bakery, your percentage of your total profits that came from selling pandesal. This would be what you do. You get your total profit. You get your profit from your pandesal. You put that over that, and then you would get the profit from pandesal over total profit times 100%, and then you'd have some percentage of your profit was pandesal. This percentage composition is useful, very useful in chemistry, but also is very applicable to other things. And so it's just a mathematical thing. So what is the percent composition of calcium hydroxide? Of calcium and calcium hydroxide. So we have, again, the same sort of equation. We have atoms of an element. In this case, it would be calcium. Atomic weight of calcium is 40, I think. Formula weight of the compound then would be, so this is 16 for oxygen, 1 for hydrogen, so 17. 17 times 2 is going to be 34. 34 plus 40 is 71. Okay, yeah, or 74. So I was right. Okay. So the atomic weight of calcium is 40. So here we have, we used the same equation that we had last time, percentage composition. So atoms of an element for calcium is going to be 1. Atomic weight then is going to be 40 or thereabouts. I don't remember any decimal places yet. And then this is going to be 74.1, which is from here. Okay, so there, 1 times 40 over 74.1 times 100% gives us the calcium percentage, which is 54.0%. Then we'll do it for oxygen and hydrogen. Okay, the question is, do we use 3 sig figs for this? You see, I don't have the question here, so I can't actually give you an exact answer. They did, but I don't think it's important here because you're not asked. Usually you need something to base it off, and usually that basis comes from the question. So for example, if the question included formula weight of calcium hydroxide is 74.1, then in that case, you would use 3 significant figures. But if the question is like this, so what is the percentage composition of calcium in calcium hydroxide? No, there's no real, like, there's no sort of indication of how many significant figures you're supposed to use. So this is not really an exam question. It's just sort of an example of the methods. Oxygen then. So I don't want to cut you. A standard for what? So I'm being asked for our class, will we have a standard in case? What is? Number. Okay, a standard number of significant. No, there's nothing there. So like for example, here you could write 54%. If you wrote 50%, that's not really as accurate as it could be. Like you could definitely get 140 and 74. So 54% would be fine. 54.0% would be fine. Because like most of the questions that you would get like this will have multiple choice, and one of the answers will be correct, and the others should hopefully not be correct, although potentially plausible. It'll usually be obvious which one, and you won't have to worry about significant figures in that case, assuming it's not given in the question. Usually it's given in the question, like, you know, the mass is 12.0 grams, so use 3 significant figures. Or the formula weight is 74.1 grams, so you use 3 significant figures as well. Okay. All right, so percentage of oxygen, so atoms of oxygen times atomic weight over the formula weight of calcium hydroxide times 100%. So it's the same as the calcium one before. So we fill in, so we got 2 oxygen atoms, 1 times 2. 2, atomic weight is 16, formula weight of calcium hydroxide is the same, still 74.1. So it's 2 times 16 over 74.1 times 100% will give us a value of 43.2%. Then for hydrogen, you do the same thing again, and percent composition. So it's atoms of hydrogen, atomic weight over formula weight of calcium hydroxide. So it's 2 times 1.008 over 74.1 times 100%. Usually, like if you're given a periodic table in your exam, you're expected to use the periodic table you're given. We'll most likely have a standard one throughout the course. You haven't needed it yet because we haven't done any like quizzes or long tests yet, but you'll be given one eventually. And so that will have masses written on it. So for example, if the hydrogen mass on your periodic table that you're given to use in the exam is 1, then use 1. If it's 1.008, then use 1.008. That should be your reference point for your atomic masses. Okay, so we then add these together to check to see if we have 100%. We don't have 100% in this case. The reason for that is because of rounding. So we have rounded up all of these answers. If we kept a more exact answer like this one, we would have gotten 100%. But because we rounded up and then we used the rounded answers, our sum is not going to be equal to 100%. empirical versus molecular formula. So empirical formulas show only the simplest ratio of atoms in the formula. Ionic compounds are represented by their empirical formula. Molecular formulas show the actual composition of a molecule. So what does this mean? So for example, we have sodium chloride, NaCl. So say we have a kilo of sodium chloride. That is a lot of sodium chloride ionic compound. So we wouldn't say we have like Na1000Cl1000, something like that. We just say we have NaCl. We assume that the whole thing is pure sodium chloride. And so this is an empirical formula. If, for example, we had hydrogen peroxide, that's a molecular formula. But it could be described by an empirical formula, which would be HO. So that's the simplest ratio. But that's not the actual molecular composition. This is the actual molecular composition, H2O2. So consider the ones below, if they are empirical formulas, molecular formulas, if it's both an empirical and a molecular formula. So H2O, is it going to be an empirical formula? So we'll just write A, B, or C in the chat. If it is going to be an empirical formula, if it is a molecular formula, or if it is both an empirical and a molecular formula. All right, thank you for those answers. B is RC. Thank you. So it is in fact C. So it is, you're right, it is a molecular formula, it is a molecule, but it is also an empirical formula because it is the simplest ratio of these that describe the actual unit. H2O2 is only a molecular formula, as I showed you in the previous page. And then HO is what? Okay, I see some people are writing A's. I think like it can be both an empirical and a molecular formula. For me, no. What I'm saying, of course, it's an empirical formula because HO would have to be a hydroxide. It would have to be negatively charged if it was going to be a molecular formula. So yeah, it's an empirical formula. Okay. And then here we have glucose. So it's C6H12O6. Is this going to be an empirical formula, a molecular formula, or both? Yep, you're all right. Everyone gave answer B. It is a molecular formula indeed. The empirical formula here, coincidentally, you have to divide this by 6, so you get what? So you'd have CH2O. That would be the empirical formula. So deriving an empirical formula. So the steps involved here are to first convert the mass percent to mass. So for example, say I had 70% of hydrogen in my sample. I would take it as being 70 grams in a 100 gram sample. So convert, first of all, the percentage to a mass, then convert this mass to a number of moles. Then from that moles, we find a ratio of A to B, and then convert A to B to a whole number ratio, because we got to have a whole number of atoms, kind of half of an oxygen. So this might seem very abstract right now. That's because it's just a schematic of what to do. We're going to do an example. So magnetite is composed of only iron and oxygen and is 72.36% iron by mass. What is its empirical formula? Okay, so what's its simplest formula? So first thing to do is to convert the percent composition to mass. We assume 100 grams as our basis because that's the easiest. Because if you've got 100 grams of the sample, then you have 72.36 grams of iron here. So that means we would have 72.36 grams of iron. Convert this to moles. So that will be what, 72.36 times 1 over, what did we say earlier? 56 was the relative atomic mass of iron. So 72.36 times 1 over 56 should be about 1.29, as far as I remember. 292 maybe. Okay. Then next step is to simplify the mole ratio. So we then, okay. So we know also, so okay. We can also, so this was iron on this side. We have to do oxygen on the other side then, over here. So oxygen is going to be here. So the magnetite contains only iron and oxygen. And so since it's 72.36% iron by mass, that means the other, what, 27.64 gram percent must be oxygen. So we have to have, what, 27.64 grams of oxygen, which is, can somebody tell me how many moles of oxygen I have if I have 27.64 grams of oxygen? Similar to this. Oxygen is 16 RAM. .727. Okay, that seems about right. 1.727 moles of oxygen. Okay. All right, so then we have a mole ratio now of 1. So for every iron over oxygen, we have 1.292 divided by 1.727. Sometimes these look like actual numbers and sometimes they don't. Is equal to, I feel like I'm getting better at this now. What, about 0.75. So that means for every 1 oxygen, we have 0.75 irons. So in order to make this a whole number, we have to, so 0.75 is the same as 3/4. So in order to make this a whole number, we have to multiply by 4, which means that we'll end up with 3 irons. And then we will have 4 oxygens. The reason why we have 3 and 4 is because for every 1 iron, so for every 1 iron, we have, or sorry, for every 0.75 irons, we have 1 oxygen. So in order to get 0.75 to a whole number basis, we have to multiply by 4 and we get 3. So times by 4. Okay. We have to do the same thing for the oxygen. So, but 1 times 4 is only 4. So we end up with Fe3, it should be Fe3O4. So, which is the same as the answer here. The reason why they have it as 1 mole to 1.33 is because what they did was a ratio of oxygen to iron. So they flipped this on its head. So instead of it being 1.29 over 1.727, they had 1.727 over 1.292. So they did it the other way around.